Okay, we're delighted to finish the day up with Emil Prodan talking about frustration-free models.
Thank you. I want to thank the organizers for making this wonderful workshop possible and giving me the opportunity to speak here. This is a work in collaboration with Danilo Orgito and Tom Stoibers, and the details behind this work can be found now on arXiv. It was just posted last night because our paper was on hold for almost a week. I'm not sure. I'll go back to the microscopic picture of phases of matter, and frustration-free models are very nice. We feel comfortable working with frustration-free models, and whenever frustration-freeness is not there, we encounter quite big difficulties.
Yeah. Here is more general than commuting project model.
Yeah, it's more. That's right. Very good. And in fact, most of the well-understood models are frustration-free, and it's no surprise there. And even though, given one frustration-free model, we have all these techniques. Maybe we understand classes of frustration-free models. Global questions still don't have adequate answers. For example, do we have a quantitative assessment of how large the pool of frustration-free model is? So here we would like to have some sort of density theorems, and these density theorems must be formulated in certain topologies, and there is no preferential topology on this space of frustration-free models, and you'll have to do the best you can and obtain stronger and stronger results in this direction. Is there an intrinsic description of frustration-free ground states? What I'm saying here is, if we are looking at the state space over our quasi-local algebra of observables, can we point to those states which are ground states of a frustration-free model? Or do we have such an intrinsic description? And I have here the third questions, which were my main motivation where I started this study. And it might sound a little bit strange, maybe to this audience, so I took a slide to tell you why I am fixated on this sister algebra. So the picture, we are in a lab or in a situation, we will always be dealing with an AF algebra of quasi-local observables. That's what we can do in the lab. But the interest is in dynamics. The dynamics is generated by a Lie algebra of almost inner derivations. And if you have double-sided ideals, then these derivations drop to quotients, because double-sided ideals, it's so happened that sometimes, when you drop the derivation, it becomes bounded, and in that case we have a well-oiled machinery to actually generate this smaller C-star envelope. And if this A accepts a filtration by such ideals, then we can even characterize this almost inner derivation. So you could say that I am biased by the success of this program, summarized in this last line. The program only works when you have this filtration of ideals, or when you restrict yourself to such a quotient subalgebra. For example, this is what you do when you do single particle analysis, you caution all the higher body sectors in your theory. And for the quantum spin algebra or full CAR algebra, which are simple, of course, this will not work. In this paper, we observe that it works for GI CAR, which is the subalgebras elements which are gauge invariant, and in that case, such a filtration exists, and this whole program can be implemented. So in the absence of this filtration, we have to go back to the drawing board and look back to these almost inner derivations, and of course the good starting point will be the frustration-free ones. So let me remind quickly the setting. So it's just a quantum spin algebra, but that Bruno introduced, and it's no difference here than there, except that I am insisting that the lattice is actually a Cayley graph of some discrete and finitely generated group. And this is because I want to have this canonical action of this group on the space of finite subsets, on the space of finite subalgebras, and even on the spaces of states and pure states. These local subalgebras, of course, give, if I have to complete them to get my local, the quasi-local observable algebra, and I want to make here a comment that whenever you see something like this, you should see a lot more. So we are saying here that we are presenting a filtration of our quasi-local algebra by finite dimensional algebra. So this already gives us a Bratelli diagram. So Bratelli diagram for the FA algebra is connected to such a filtration. And right from the beginning here, we pick a very specific filtration. So this these filtrations will appear again and again, and that's why I want to make this this comment.
So S there is some arbitrary dimension?
Oh, S should be a full matrix algebra of finite dimension here.
Some finite. You don't care which one?
I don't care which one yet. So we learned from, so we heard from Bruno that if we work in thermodynamic limit, Hamiltonians don't make sense, but dynamics still makes sense. It's a one parameter group of automorphisms, and the generators of that dynamics is an almost inner derivation, which can be cooked up from these nets of inner derivations through standard limiting procedures. I should mention the fact that all almost inner derivation have this dense subalgebra in their domain, which is a core for these derivations. And then if you restrict to these cores, then the derivations can be composed, and you see that under the commutator they remain local, and this is how you cook up this Lie algebra of almost inner derivations that we have to battle with. And I have here, so when we talk about frustration-free models, all this, I mean, the element Q, which is repeated, translated and summed up here, it's a positive element. And even so, 0 belongs to the spectrum of this inner element, H lambda, which should be thought as a local Hamiltonian. So this is a special property, and if you throw in, of course, random queues, this property will fail more often than not. And moreover, if you have a frustration-free model, then one will say that a state it's called frustration-free if it annihilates this all the elements which appear in the sum of the derivation. So,
could you give us some intuition about why this condition has something? Condition seems to be that zero belongs to the spectrum of the local Hamiltonian. What does that have to do with frustration class of spin models?
oh, the geometric frustration, you will say. So here you will say that it's some sort of a spectral frustration where if you have terms like this and each of these terms is positive, then you look at the spectrum of this. Typically, you will find that the spectrum actually moves away from zero. And in fact, the larger you take this lambda, the further the spectrum is away from zero. So it's a very special case in which the spectrum actually it's anchored at zero.
Let's see, I mean, if there were an operator that conjugated h to minus h.
So this is just an element, let's say a product of spin operators, and then you just translate and put them like so. Suppose this one were chosen to be positive. You will not, the spectrum of this operator usually will move away from zero.
Let me ask a better question. Could you give a simple example of frustration free?
Yeah. All these are frustration free. Yeah. No, yeah. So these are all frustration free models. And so these are unbounded derivations. They cannot be defined over the entire algebra. So it will be nice if we could actually work with bounded things. And here is the good news that we in fact can do that. So if you take P lambda to be the support projections of these local Hamiltonians, then they have very special properties, and even more, okay, being projections, they are bounded, but even more if one is given us the support projections, then we can derive easily frustration-free models. So there is sort of a nice relation between models and this family of support projections. So we put up then a definition here that shifts the focus from derivations to families of frustration-free projections. What are they? So first, it's an increasing net of proper projections indexed by the set of finite subsets of the group. Each P lambda is localized in each in its local subalgebra, and they obey this equivariant relation with respect to the group action. So I will neglect this part and call the set of all these objects by this symbol, and one will quickly learn that you can organize this in a semi-lattice with respect to a natural order of projections. So, so we were very happy to have such a good definition, focus our study on these objects. But then when we had to say something non-trivial about them, we kind of felt like we are in a vacuum. There was no tools to look at this. And it's always happen in mathematics. You like to make connections, and you make another connections until your original questions actually become trivial. So I will introduce now three objects which are exist in the world of sister algebras. So it's the hereditary sister algebras, and I'll introduce them to you through a detour through the left ideals, which are known to this community via the GNS representation, where we start with a sesquilinear form like so, and we would like to transform our local algebra into quasi-local algebra into a Hilbert space, and to do so we need to quoting out the bad guys, and the space of this bad guy turn out to be a closed left ideal, and this one is canonically associated to the state omega. And why work with left ideals when you can actually work with nice sister subalgebras? And here, when hereditary sister algebra enter, intrinsically, this is the definition. We have B inside of larger A, and if this A is from larger A, and there happens to be a B which is on top of A, and this B is from the hereditary algebra, then necessarily A is in B. So this unassuming property, in fact, endows hereditary sister algebra with quite fantastic properties which will appear along the top. So we can pass from left ideals to hereditary subalgebra because there is an isomorphism between the two posets. So I will use this symbol from now on to specify or to indicate the space of proper hereditary subalgebras of a sister algebra A. So here is why is this so now I have a state, I can compute the null state, take this intersection, get a hereditary algebra. Why is this interesting? And at the first sight, even without the analysis on the next slides, it's I will say it's for a sister algebra, it's actually very very appealing. In Bruno's talk, the space of states was studied externally. So you go through GNS representation, which is takes you to von Neumann algebras and so on. But here we can stay in the world of sister algebras and study the space of states from inside. For example, you can, the vector space in the GNS representation is nothing but the equivalence class of the unit in when you take the quotient by the null space, the null ideal. So then B omega enable us to unpack this vector state to an AF sister algebra. And then homotopies of ground states induce homotopies of this hereditary sister algebra. So now we have homotopies of closed subspaces, which already moves in a topological space. So it's another way to look at the homotopies of states, and this everything inside the quasi-local sister algebra. Also interesting, automorphic equivalent states have isomorphic hereditary sister algebra. So that's also a positive thing. Now I'll mention a connection which is known between hereditary sister algebra and the subsets of the space of pure states. This is standard. So if we take a state from a pure state, then its corresponding hereditary algebra, it's a maximal proper hereditary algebra, and there is a bijections between over there, and even more if you take an arbitrary, let me say, so if I take a hereditary algebra, and then I am looking over all pure states for which there B omega sits on top of this, then I get a subspace, a subset of the pure states, and I even have the other relation. So at the end, there is an lattice isomorphism between hereditary sister algebras and the power set of the pure. So we can use hereditary algebra to investigate the state space of pure states. And for example, given a state, not necessarily pure, you can go to the hereditary algebra, and through this map you can get a subset in the pure state, and this subset will be called the support of omega, and you can define a support of omega without using the extremely technical disintegration theory, which in terms of a state, in terms of a pure state. So, and I'll have to say one more word. There is a nice characterization of hereditary subalgebra. It's always of this form. So there is a positive element from the algebra itself, and B always come as a sandwich with this WB, A, WB, and closed in the topology of A. And furthermore, this W can be chosen in this way, where 1 is an approximate unit. I should say that every proper hereditary subalgebra doesn't have a unit, so we are talking about sister algebra without a unit. And moreover, if W is chosen to be unique, then this W, if B is finite dimensional, then W can be chosen in a unique way to be a projection. Okay, so this, now I have two objects that I introduced. So now it's the time to introduce the open projections, which live in the double dual of the sister algebra. And here is the definition given by Upman, 1969. So his motivation was the following. So he was looking for the equivalent of topology in non-commutative spaces. So if you have an open set, you can look at the characteristic function over that. Of course, it's a discontinuous function, so it's not in the algebra of continuous functions, but it is in the double dual of that. And this characteristic function you can construct it by limiting procedure of smooth functions. And if we are restricting to commutative sister algebra, then this is precisely how these characteristic functions over open sets arise. So he gave this definition of open projections and show that okay, these concepts exist in non-commutative sister algebra, and a lot of facts that occur naturally in classical topology are reproduced at this level. It turns out that this is also a semi-lattice, and moreover, there is again an isomorphism between the posets of open projection, space of open projections, and space of hereditary algebra. So the picture is like this. So we have this isomorphism between posets, and since the proper projections, it's a net, it's bounded, therefore it has a limit, I can hook the space of frustration-free models in this way. So from this side, not entirely satisfactory, because we gain something out of it only if we somehow we can characterize the image over here in an intrinsic way, something that is independent of models. And so here we go. What we discover is that if you take B, a proper hereditary subalgebra, then you can take the intersection with these finite local algebras. You get again a hereditary subalgebra. Therefore, it should be of this type. So I just told you that it's always a sandwich, and if this happens to be finite dimensional, then you always have projections. Okay, this is always the case, but if additionally B displays this property F written here, then these projections are approximate units for B, and it's also a frustration-free proper system of projections. So that's the intrinsic characterization, and I put here a few words. So when we discover this property F, since our total algebra is already filtrated by this S lambda, you might think that this one is trivial. Any B will even any subalgebra will have this property. And working simple examples, we convinced that in fact actually this one is very special. It actually fails more often than not. And what we have here now is that this property F is intrinsic. That means I can identify now what a frustration-free system of projection is, even if I move from this algebra, even if I take other filtrations. So it means now we sort of in our thinking we found the essence of frustration-freeness. Why? Because we can recognize it when we move from one context to the other. Now, provided, of course, that if this construction gives us all frustration-free system, and it does. So this is the thing which assures us that we can go from hereditary subalgebra with property F to frustration-free model projections and back. So this now is the complete picture that we wanted, and we have a intrinsic characterization on this corner, and I will go back and answer some of these questions. For me, it's very exciting. So there are various tools which enter in this diagram. So think over here. Soon I will talk about the Cuntz semigroup, which hooks in this corner. Over here, these are AF algebras. So think here about Bratelli diagrams. And here is where the techniques Bruno presented. So now they are all together in can be analyzed from so many different angles. And for example, if I have a state omega from here which displays frustration-freeness, then I have this preferential filtration. Therefore, there is a Bratelli diagram. This is a first time you see that to a state you can associate a Bratelli diagram. And if this was known to us a year ago, I would have told you what is this Bratelli diagram for Kitaev, the Tori code, for example. I cannot wait to calculate what this Bratelli diagram is, what this local automorphism do to this Bratelli diagram, and so on. See, So I'm going to density.
Yes, that last page there. So you have. Is there any kind of choice there that you're saying, like, so you,
Okay.
does preferential filtration rely on some kind of choice that you've made?
We already started with this filtration.
Uh-huh.
And that property F, which is the essence of frustration free, picks up the filtration. So as I mentioned, to have a Bratelli diagram, you have to specify this filtration, and here it comes. So
Finite subsets.
these are finite, that's right, finite subsets. So now moving to density theorems, and here I will highlight again these special properties of hereditary subalgebra. So I'll walk you into this statement from a different point. Suppose you take a B, a subalgebra or of an AF algebra, and you will say, well, suppose that B happens to be AF algebra, therefore it should accept the filtration, call it this Bn, and then you'll say, well, I'm very sure all this filtration will lift to a filtration of A. That was exactly what we were supposing, only to find out that that actually fails miserably, and it's only true for hereditary subalgebras. So if you have a hereditary subalgebra of a separable AF algebra is immediately AF algebra, and any filtration of that hereditary subalgebra lives to a filtration of A. Quite amazing. This is a statement, classic statement on AF algebra, which says that if you have different filtration, in this case some arbitrary filtration AN, and this one is our preferred filtration, and there is always a U as close to unit as you want, a unitary element, such that these two algebras are the same without closing. So now if you put these two together, we can understand the hereditary algebra which have frustration-freeness, how many of them are inside the set of all frustration-free, and here it is. So it means that if you take any hereditary algebra, think of you take any state gives you a hereditary subalgebra, you can twist it by a unitary element from the quasi-local algebra and make it frustration-free. So in other words, this tells us that there are many. The frustration-free models are quite many, but there is a catch. So in my discussion with Professor Wen, touch on this subject where you say how, if you don't have a frustration-free model or thing, how if you conquer it patch by patch, and if you look how this U is constructed, it's exactly constructed in that way. So you conquer, you move it little by little, and on the next slide, I will tell you that you can do that, but you will break the G invariance. So it's a caveat over there. I can also formulate a density theorem in terms of open projection. So this is the image of frustration-free system of projections, and they are dense in the set of all open projections, and this is even in the norm topology of V of H. So this, for example, you can see it as a strengthening and generalization of the known fact that matrix product states are dense in the weak star topology on the pure state. It's much stronger, and so some thoughts. So one hope of mine was that I can anchor into frustration-free models, and I will take I will take this set and close it in norm and get a nice C-star algebra. That seems not the case because then we will cover physical and non-physical states. So it's quite clear that G equivariance or I mean some sort of G invariance or G ergodicity must be imposed to actually get, and this is indeed we get here. So the fact that we have topological insulators in one particle is precisely because we require some sort of constraints on the models. Now, open projections can be compared in a natural way by the Cuntz semigroup. So Cuntz semigroups were introduced long time ago as a device to study C-star algebras which don't have projections. So as an alternative to K-theory, K-naught theory, which anchors on its projections. And in Cuntz semigroup compares positive elements, so there is an equivalent relation of positive elements, and it was this is relative recent in the world of operator algebra, was observed that Cuntz semigroup also classifies open projections under a very natural comparison comparing equivalence. And Cuntz semigroup has been revived recently because for quite a good classes of C-star algebras, including AF algebra, if you have an isomorphism of Cuntz semigroup, then that isomorphism can be lifted to isomorphism of C-star algebra. It's a very important tool in the program of classifications of C-star algebra. So it's very difficult to calculate, and I remember a nice workshop we had in Münster. Wilhelm Winter asked me if we were all hooked so much in K-theory that we couldn't see that these tools from the program of classifications of C-star algebras are of any use in topological insulator, topological phases. And now it's very interesting. It looks like physics will have to say something about that program. So here it is. So this is the Cuntz semigroup of an AF algebra, and you get this monster which for C-star algebra it looks like a nightmare because this is the complete topological invariant, and as you can see it's not quantized, it takes continuum values. Nevertheless, if you compute the same group for another algebra, it comes to be this, then the two are isomorphic. But this computation includes non-physical states, so it's quite interesting to see where the frustration-free models live in this group. Either way, it will be extremely interesting. So either any class in the equivalence in the equivalence class of a Cuntz group can be represented by a frustration-free group, in which case we remain with the same group, or parts of this continuum is fraction, and now the invariant takes quantized value. So that's a question to remain to be open. And how about G invariant ones? And talking to Corey, I learned and then I Googled and found an equivariant form of the Cuntz group, and that gives us another hope that this actually will come to be a countable set. So that's also an interesting direction. So okay, but something even more interesting. We don't want to look at the Cuntz group on this. Actually, we would like to look on the Cuntz group on the hereditary subalgebra. So now we take an algebra, a state. Through the state, we have a hereditary subalgebra, and I can compute the Cuntz semigroup. as I said, if automorphic states have isomorphic hereditary subalgebra, they should have the same semigroup. So all these locally equivalent, local automorphic equivalent states should be characterized by the same Cuntz semigroup. And what that is, again, it's very interesting when you.
I think I missed it. What is the definition of the Cuntz semigroup?
Yeah, I thought I will not get over it. If I write on the blackboard, people over there might not see. So we say that A and B from the positive cone of the algebra, and we say that A is a funny sub-equivalent to B if for each epsilon there exists an R in the algebra such that RA R star minus B is smaller than epsilon. Smaller than epsilon. And then it's equivalent if the opposite goes about. The Cuntz semigroup will be the algebra A. You have to stabilize by the complex, and you take this equivalence. Cuntz semigroup has very special properties, so it's a very specific it's an order group, and it's a subcategory of semigroups. And now we have a functor from sister algebras into the Cuntz, into this category of Cuntz semigroups. The functor is not so nice, so it doesn't give you spectral sequences, so on. So that's why computing the Cuntz semigroup is much more difficult than computing the KK theories. So intrinsic characterization of ground states. This I spent 1 minute. I was trained in Romania in spectral theory and came to US, and at some point I landed in Santa Barbara, and there people were talking about ground states with very interesting properties, correlation function, but with never mentioning a Hamiltonian. So for me it was very confusing. So the thing was, okay, we are talking about states, and if we cannot construct a Hamiltonian for which this if state is a ground state, it's unphysical. So that was the point of view. But now, can we characterize these states intrinsically? Because if you just go like what I said, you go in circles. So can we characterize such states intrinsically? And for the class of frustration-free ground states, I'll tell you that yes, we can. So take an omega, a state, and we say that it's a frustration-free ground state if there exists at least one frustration-free system of projections, such that these projections are annihilated by the state. And we learn that out of this system of projections, we can cook up frustration-free models. And this condition is the same as saying that, yeah, there is at least one frustration-free derivation for which this is a ground state. So now, this is how you will characterize these states. So if the hereditary sister algebra B omega associated with the state display property F, then omega is necessarily a frustration-free ground state for a frustration system of projections, which can be canonically derived from this B omega. And then a state is a frustration-free model if and only if its support contains the support of a state displaying property F. So that was my slide. I see I still have 10 minutes. So now I thought what I will going to say now will be in the question session. So I'll say it anyway. So how about the anion sectors? Where and what do we do in this picture? So yeah, the local automorphisms, I mentioned them several times. They should have they should have precise actions of these Fratelli diagrams connected to these p omegas, and those need to be studied on specific models and so on. But there is an even bigger conceptual difficulty, which you don't notice unless you try to be context free. So what are these cone algebras when you work on a Cayley graph of a group? Suppose we are talking about the free group. I think everybody knows how the Cayley graph of the free group with two generators is kind of fractalish. What is the cone subalgebra? So in Peter's talk, he used the fact that his lattice is embedded in a space. In Kitaev conjecture, this space is just a topological space. It doesn't have geometry, but there it was endowed with Euclidean geometry, and that's why you can define the cones. So how can you define this cone algebra in an intrinsic way? Maybe the hope will be to be only the AF algebra and perhaps a filtration you should use to define these cone algebras, cone sum algebras. At this point, it looks like the group action is important. So there are these cone semigroups when you have a group. And with Danilo and Tom, we just finished a paper on how things can be complicated when you get a square lattice and you take edges which are incommensurate with the lattice. So there is a lot of things that can come out, which is at the border with the quasi-crystals and stuff. But that's what we would like to see. So if you have an AF algebra which comes out of, let's say, an electrical circuit, these qubits are not arranged in any physical geometry. All you know that you have this AF algebra. Okay, where are the cones and how do you define the sectors? And do the sectors actually depend on your choice of cone algebra, subalgebras, and so on? So these are questions which popped up while studying frustration-free models in this in this approach. So I'll stop here and thank you very much.